Hey everybody, this is Bruce and the dog on the floor, and today we're going to be building a linear regression, or at least starting to build one, using Elixir. And this is the first step of learning how to build machine learning models, or at least how to understand them. But before we get going, I'd like to review what we learned and talk about the individual tasks that we're going to do in Elixir. So remember, first, what we're actually doing is we're actually building a line, or which is a prediction. And normally we're going to start this with just random parameters like this $10,000 here. And then we're going to build some type of a formula based on that. And then over time, we're going to adjust those parameters so that they get better and better. So the first step is to build this linear model. And you can see that this one is, let's call it M times the years of experience. Let's call that X. And we may have some type of fudge factor, and we'll call that B. But in this example, we'll just have the fudge factor or the bias always at 0. And so based on these individual observations, you can tell that, for example, the line over one of those points on the left-hand side is pretty far off. And on the right-hand side, it's also far off, but in the opposite direction. So what we're going to do is build a loss function. And the only job of this loss function is to get much worse when the line does not fit the curve exactly across from one end to the other. And by the way, it gets much worse if the line drifts from a cluster of points. So this type of loss function is going to let us play some games with calculus. So this type of loss function is called the mean of the squares. So all we're going to do is we're going to take the prediction at the salary value and then find out how far the salary is from the actual data, right? So if there's a particular experience point, then we can find out exactly how far that is at an individual value. And then what we can do is take the squares of all those, then add them together, and then divide by the number of them. And that's going to give us an objective calculation. When our line gets worse, it's going to get the loss is going to grow very quickly. And when the line is better, this function is going to return a much smaller value. So what that allows us to do is play some games with calculus, and we can take the gradient. And the gradient is just a line that kind of connects with our loss line, and say that we've chosen an experience point of 8,000. And that's really too high for this particular curve. We can tell that because the shape of the slope line is going up and to the right very steeply. And so what we're going to do is we're going to send our prediction to the left, and we're going to send it in large steps if the slope is steep, and small steps if the slope is small. And essentially, if things are going up quickly, then we'll send them in the other direction. This process is called chasing the gradient, right? Okay, so in this case, we're going to make a prediction, then we're going to make other predictions. And as the slope changes and gets smaller and smaller, we're going to be getting closer and closer to the minimum point at this curve, which is the prediction that we're looking for. That's when the loss is least. And what that's going to allow us to do is take smaller and smaller steps as we get closer and closer to the answer. So the 3 steps that we have to take, we have to build that predictive line. Then we have to build a loss function. Then we have to find a way to update our parameters, that one in orange, which is just a single number now, but it's also going to work with tensors, so that if we were working on, for example, the price of a house, we might have several values, like the square footage of the house, like the number of bathrooms, like the distance to a main employer, and things like that. So that's what our Elixir code is going to look like. And what we're going to do in this section is open up a live book, and we're going to start this process with NX, and we're going to code up that formula at the bottom, our predictive model, to start with. and then we're going to work on a loss function. So that predictive model is going to be something like mx plus b, right? And if you've been thinking about your high school geometry or even your college geometry, that mx plus b is really the formula for a line, right? And we're going to be able to plug in those parameters at m and b and actually build something that we can start to build predictions around. So that's what we're going to do next. So we're going to base our implementation on one built by Sean Moriarity, the creator of NX, with Jose Velen. So we're going to start by looking at this basic linear regression. And remember, in this video, we're going to look at the first two steps. So the first two steps are first creating that predictive model, and second, calculating the loss based on that model. And we're going to do that work within def-in functional definitions so that we can pass them tensors and return tensors from the implementation. So it's going to go in a module called linear regression. And then we're going to add our predictive model. And here's our first def-in. So to make a prediction, we take the arguments. Remember, we're going to predict mx plus b, and m and b are the constants that we're going to tweak. Remember, this is a configurable function that makes a prediction, and the things that nx is going to tweak is going to be m and b based on the update instructions that we give it. And so if we have a model with an m and a b in it, we could build a function that returns just x, right? So what this looks like is mx plus b, right? And this multiplication we can use in simple tensor structures. We can use flat multiplication, but we're going to make one tiny tweak to this implementation. We're going to use the dot product instead, because the dot product will allow us to work with multidimensional tensors. All right, so the next step is based on this predictive function. Remember, we're saying given two constants that we're going to hone in and find the best ones that minimize our loss. That's what we're looking for. After we have this ideal grouping of constants, we can compute an x based on whatever those constants are, right? Like maybe this is the m would be the number of years of experience of a typical developer. And then we'll multiply that by some x, right? And so if this is the years of experience, we'll multiply that by some amount of time, and then we'll add in some amount of time that's based on, I don't know, maybe a starting developer's, somebody with 0 years of experience, maybe they make, I don't know, 15 to 30,000 or something like that. But based on that data, based on one set of constants, we can build a function that can predict, based on the years of experience, we can predict a salary for a developer. That's going to be a simple prediction because it doesn't take everything into account, but our future predictions can add dimensions, like what are the languages you know, and what are the other aspects that make a programmer more or less expensive, like location and things like that. Okay, so this is the predictive model, but given that predictive model, what do we have to do next? Well, we have to compute the loss. So this is the loss function. So given the parameters, right, that m and the b, right, so that's some length of time to multiply by years of experience and some initial length of time to kind of add in, we can make a prediction. And so I'm going to make the prediction based on some x. This x can essentially be a whole matrix of data points, right? So that's going to be in the form of a tensor. So I take all of those data points and I take the parameters and I make a prediction, which is again going to be a tensor. And then what I do is these predictions are going to be compared to the actual values. And then, so say this one is off by $1,000. Well, I'm going to square that. And then when I'm done with computing a bunch of squares, I'm going to take the mean and just build an average of all of them. And that's going to give us our loss function, which will accelerate rapidly as I drift away from the actual data, right? And that's what you want. And so after we build this couple of functions, then we'll be able to iterate over things, and that's the subject of the rest of this article. I've gone ahead and created a project called Linear to hold our linear regression. And this is what I've done in the mix.exs. I've added the nx dependency, and as of this recording, we're still working on the GitHub dependency. And then we're doing a sparse fetch, and this is a GitHub dependency, not a hex dependency. Everything else is the same. And then I did a mixdeps get and a compile. But so let's go ahead and start working on this application. So I can work in a regular Elixir module. And right now, I'm not going to do any acceleration to start with. But what I'm going to do is do an import of nx. And I'm going to go ahead and keep the names of nx functions namespaced just like nx. So I don't need to do anything there. What I do need access to, though, is the defn macro, because the defn macro is going to be what allows me to actually implement numerical definitions. And so the next step that I have to do is to build a prediction. And so the prediction looks like this: defn predict, and then I'm going to take my model. And remember, the model is the thing that's going to build that line. And so the line is going to have two different pieces in it, but I kind of want to keep those two things together and separate, if you will, right? So the first thing is going to be the m, and that's the slope of the line. And the next thing is going to be the bias, which is actually the y-intercept, right? So if you remember your high school geometry, this y equals mx plus b is what we're after. If you don't really understand what's happening there, don't worry. All it is these are the components, the constants I need to compute a line where if I give it x, it can give me the line with this particular slope, this high or low to start with, right? And so one of the things that I could do is I could say m times x plus b. And this is, remember, this data might be a tensor. And in fact, it very well will be a tensor if all that we're doing is just taking single dimensional data, right? Even if we have multiple observations based on that data, this is going to be a whole chunk, right? But maybe what we want to do is have two-dimensional data here, so that has features or something like that. So if you remember in the Julia language, or if you're a machine learning aficionado, what you understand is that sometimes there are features, and we keep features in one dimension, and we keep observations in another dimension. So what we're going to do is do an nx dot dot. Instead of making this a multiplication, we're going to make this a dot product operator instead. Because remember, a dot product operator is exactly the same as multiplication for one-dimensional tensors. All right, so let's take a look at what the loss function looks like now. So now all I have to do is build a function, and this function is going to be based on the parameters of the model. Remember, that's the m and the x, right? So I'm going to label this. So I'm going to say this is the mx plus b. So this is the m and the b, right? This thing here. And I'm underscoring this because we're not actually going to use them. I just want to label them so that we can remember what's going on, right? So the other thing that we need to make a prediction is the X, right? What's the experience value for the employee that we're going to use to predict what were we computing before? We were computing the salary, right? You give us the experience, we'll compute the salary, right? Okay, so now what we want to do is we want to take the actual, or no, we're going to take the prediction, and the prediction, well, we already know how to do that, right? So based on X and the params, all we have to do is pass these params and the X, right? Okay, cool. So now we need to take the average or the mean of the sums. So, well, first things first, we need to compute the difference between the actual observation and the prediction. So that's pretty easy to do. We could say the difference is the actual, right? So that is the, oh, and we also are going to need a Y value here, right? So for some salary and a value. So these are real values. So I could take the actual, let's call this actual, and let's call this the predicted Y. So let's say actual Y minus predicted. Let's take those and group those together, right? And so what do we need to do? We need to square them. This is a pipe, right? And then we need to process the mean. So the mean, or actually so essentially I'm getting an X and an actual Y. I'm just going to call that Y. And okay, so what's happening is I'm getting actual observations here. And so for all these observations, all I have to do is take Y and subtract the predicted value from them. And then I get some value. And then our loss function is raise them all to the power of 2 and then take the average. And that's it, right? And so let's see how this runs in IEX. And we'll do that next. Okay, so let's try this much out. So I'm going to go IEX, smix. Okay, so what we're going to do, remember we have this function called linear.predict, and the prediction takes a model and it takes an X value. So let's get the prediction at 2. So the model is really two things, right? Remember it's mx plus b, so we want to provide an m. So let's say the m is 3 and b is 10. So this should be 3 times 2 plus 10. So that should be 16. And that's what we get. We get a tensor with 16 in it, which is pretty cool. So we can provide tensors in here, right? So this is a scalar now, so that's an individual value. What that could be is an entire matrix, right? Or at least a row of one that really constitutes a full observation, right? So that could be the house price, the square feet, the number of bathrooms, the number of bedrooms, and so forth. And this would also have to be tensors to kind of match that output, right? So since we're going to multiply these things, that's a dot product, or this has to have the same number of columns as the rows in this tensor. But right now we're using scalars, so this is just going to work for us fine. Well, what about loss though? Let's do that next. Okay, so this is what our loss looks like. The API looks pretty similar, right? We have to take an M and a B in our model, right? The parameters for our model. These are the things we're trying to hone in on with our machine learning. And then if we feed it X, we should get Y out of this thing. And the loss will determine how far away these things are, right? So I can send in not just one computation, but several computations, right? So for example, I could do something like this. Okay, so let's compute the loss now. So I could say nx.loss, or this is linear.loss, and I can compute the same type of thing, right? So maybe I want 2 times x plus 10. And so if I'm computing the value for 3, that should be 2 times 3, and that should give me, what should that give me? That should give me an 8 or a 16. And so the loss is 0, right? But if I pass in something like a 20 here, that should give me my average loss, should be the average of the squares. So 4 squared, that should be 16. Yeah. So it's expecting 16. It gets 20 instead. So it's going to penalize me by the square of the difference between these two, which is 4 times 4, which is 16, right? And so the cool thing about this is that I can use tensors for these values. So I can say nx.tensor, right? And maybe I want to compute it for a, or actually, will this let me, let's see if we can do this, if this is just a 2 and a 10. Let's see if I do nx.tensor. Let's see if I can provide a 3, a 4, and a 5. And let's see if I can provide that gives me a 20, a 21, and a 22. So those aren't going to line up perfectly, but they're relatively close, right? So the loss is small. Here the loss is 1 squared, and here the loss is 2 squared. So when you add up the losses for all of these, the average is going to be something like this, right? So that's pretty cool. So that means that we can work with dimensional data in this spot, but we can also work with multi-dimensional data in this spot for the m's and for the b's, as long as the dimensions line up the way that I expect them to. And I can also work with multiple batches of data, and NX will do the right thing. So that's kind of what makes this linear algebra so powerful for this kind of a problem. We're going to actually work through some examples, and we'll do that in the next section. And what you're going to find out is that it's relatively simple, even when we're building the things that Axon, the machine learning library, give us from scratch when I'm working with just a simple linear regression. And that's really an excellent thing. From Bruce and the dog on the floor, this is Groxio Learning.